Welcome back to part 2 of um, recurrence relations. So this is section 5.6. I want to pick up where we left off in our discussion on the general formula for, in this example, compounding annually $100 at 7%. Now, if a few things. First is, if you're familiar with the compound interest formula, then you'll know it's some amount times, so compound interest, or I should say compound amount, because it's what's in the account at the end of the time, is the principal, initial principal that you put in, times 1 plus the rate divided by the number of compounds to the number of compounds time. Now, how does this relate to what we just found here? Well, our rate was 7%. We are compounding once a year, which is which is 1. So 0.07 divided by 1 is 0.07. 1 plus 0.07 is 1 plus 0.07 to the n that we have here. Why is it to the n? Because in this case we're dealing with n is our time. So n is the number of years that we're compounding by. So the n's are a little bit different in what they stand for from one of these equations to the other, but bear in mind that they're showing the exact same thing. So this is essentially an explicit formula for something that is a recurrence relation. Now let's go ahead and prove the recurrence relation for this. So I'm going to go ahead here and open up a new page, right? So if we want to prove that this equation works no matter what, we always have to start out with our base case. So let's not look at strong mathematical induction. Let's go ahead and just look back to what we first learned in class. Our base case is the initial value, which is P0, and we said that that was $100. Well, according to the formula, P0 equals 1.07 to the 0 times 100. 1.07 to the 0 is 1. 1 times 100 is 100. So we know that our base case works. Moving forward, let's look at our hypotheses. We will assume that P sub k equals 1.07 to the k times 100 is true, right? And we are going to show that this is true for the k plus first term. So k plus first term, just so we already have it here, pk plus 1 would be 1.07 to the k plus 1 times 100. So if we can make this fall out of our inductive step, we know that this equation will work no matter what, no matter how many years we're compounding for. So let's consider for our inductive step p sub k plus 1. Now, we know by the recurrence relation that this is equal to 1.07 times p sub k, because it's a recurrence relation. It's based directly on the previous term, and all we know right now is that this recurrence relation works, because a recurrence relation always works. Now, according to our hypothesis, we said that p sub k is this equation right here, and that it will work. So let's go ahead and substitute. So by hypothesis and substitution, we have p sub k plus 1 equals 1.07 times 1.07 to the k times 100, which if we simplify, well, this is all multiplication, 1.07 times 1.07 to the k is 1.07 to the k plus first times 100, which is what we were trying to show. Therefore, by mathematical induction, we have proven that this explicit formula works instead of using the recurrence relation.